Okay, class, welcome to lecture 3, measures of position and outliers. Um, so we got to do a little bit of summary to continue. So far we have two types of measures. So we have measures of central tendency. That was the first lecture. So various numbers that sort of act like the middle of some data. So there's the mean and the median, and the mode sort of fits in here, not as well as the others. And then there's the measures of spread. And so these tell you how far apart the data is, but sort of more specifically in the in the three cases, how far things are spread out from the mean. So the absolute mean deviation, the variance, and the standard deviation are ways to tell how spread out the data is away from the mean. So the idea is away from the middle. Okay, so now we're gonna look within the data at specific data points. So now we look at ways to measure how far a data point is from the center, so more specifically the mean in the first methods, relative to how spread out the data is. So this is what it means to measure position. So this measures position of data. But a key aspect is this word relative. So the idea is that the position of a specific data point within all the data that you have, it really depends on how spread out things are within the data. So the position is really relative to how spread out the data is. So let's look through a little example to get this idea down. So let's pretend that we have some data and the mean, we just go straight to the mean. We don't have to worry about what the actual data is. Let's just pretend that the mean turned out to be 300. And we could sort of picture this on a number line. So say that this is the mean. And then one of your data points in this data list that I'm not revealing, let's just say it's, I don't know, 350. So then the idea is 350 far away from the mean or near the mean? Well, it's all relative. So how do you know if 350 is far away from 300? Sure, it's 50 away, to be extra precise, but I don't really know if that's a lot or not if I don't know how spread out the data is. That's what we need to know. So for example, if I went and calculated that the standard deviation happened to be 20, that's saying that on average, most of the data is 20 away from 300. That's what the standard deviation does, because it measures the spread. So it's saying that the data is typically 20 away from 300. So of course there could be data that's further than 20 away, but it's just saying that on average, most of the data is 20 away from 300. So if that's the case, then that means that most of this secret data is between 280 and 320. And then between 340 and how do I subtract 2260? There's even more data, is the idea. So 350 sort of seems very far away. We're going to make this more precise later. But for now, the idea is it just sort of seems far away because the standard deviation is only 20. So because the spread is not that much, 350 seems very far away. So when I measure its position, how far away 350 is from 300, I really do have to think about what the standard deviation is first to say whether it's far away or not. So meanwhile, if the standard deviation happened to be 100 instead, then the idea is now that the data in that set is typically 100 away. So it's typically from here to here, 200 to 400. So now 350 doesn't seem so far, because most of the data is between 200 and 400. 350 doesn't seem very far away anymore at all. Okay, so this is the idea behind measuring position. And the point is that it really does depend on the spread. If things are very spread out, then further away things don't seem that far away. Whereas if things are not very spread out, then even going a little bit far seems a lot further away. Okay, so let's make this a bit more precise, make it easier to understand. Okay, that's just the intuitive understanding for now. So what we're going to do is we're going to use standard deviations as units of measurement. So by doing this, so the idea is you're going to count by standard deviations to say how far away things are. And you may have heard terms like this before. Somebody will say like, you are 2 standard deviations above the mean. You're 3 standard deviations away from the mean. But you can also be 2.5 standard deviations, 2.1. The idea is that 1 standard deviation is like a certain distance away from the mean. And we're going to count by those to make everything standardized. Okay, so what will this do for us? We can measure position relative to the spread, because the spread is the standard deviation. Well, the standard deviation tells us how spread out the data is. That's what we saw last time. But more importantly, we can actually measure position without context of the specific data, because this is going to standardize things. So we'll see how that works with an example later. And then we'll do things like this. We'll state things like, you'll hear people say stuff like this. This data point is 2.3 standard deviations above the mean. And you're supposed to hear that and say, okay, 2.3, that's pretty far away. Because most of the data is between 1 standard deviation. Okay, so let's see how this works with some examples. So just like in the first example that gave the intuition, I don't actually need data. I just need a mean So I'm just going to pretend I jumped straight to the mean. I need a standard deviation to tell me how far away things are typically away from that mean. So the idea here is that most of the data is typically 3 away from 20, and a specific data point in which I want to figure out how far away it is. So I want to measure its position. So then, to do this, to find how far 27 is from 20, relative to the spread, so it's not just 7 away, we want to think about how many standard deviations away it is. So really what we're saying is, in terms of number of standard deviations, what should we do? We do this. So first, we do just say how far away is 27 from 20. So remember, we learned distance is really just comes from subtraction. So we just subtract 27 minus 20. So that's the total distance away, not relative to how spread things are in your actual data. But if I want to make it be relative, what I do is I divide it by how big the spread is, how big the standard deviation is. So what I get is the distance per standard deviation when I do this. So that'll tell me how far away 27 is in terms of standard deviations. So 27 minus 20, that's just 7. Divide that by 3, 2.33 repeating. So the idea is that that means that 27 is 2.33 repeating standard deviations from the mean. Okay, and then this fancy number has a fancy name, just like all things do in math and stats, because to make it seem more confusing than it is. So this number is called the z-score. Specifically, it's the z-score of the data point that you're looking at. So in this case, it would be the z-score of 27, but we're just going to say z-score to save time usually. Okay, so let's just do a couple more examples just to sort of get the process down first before we think too hard. So if the mean is 60 and the standard deviation is 8, let's find some z-scores for each data point. So again, let's do it for these 3. The idea is how far away are these things from 60 in terms of numbers of standard deviations, so relative to how spread out the data is. Okay, so z for 63, people would like to use the letter z, so they do this. They say z equals, and then they just do the calculation. So 63, so you take how the data point you're looking at, and you subtract the mean, divide that by the standard deviation. So because the standard deviation is kind of big, 8, 63 doesn't seem so far away at all from 60. And this z-score, being a sort of a fraction, a small number, reveals that. So 63 minus 60 is 3. 3 over 8, you can plug that into a calculator, 0.375. So the idea is that this number being a sort of a small decimal, this tells us that yes, 63 is close to 60 relative to the spread of the data. Okay, and we'll just do a couple more. So for 51, it's going to be a little bit different looking. So I'm going to do the same thing, but you might spot something weird that seemingly happens. So I subtract to find their distance, but now I get a negative number, -9/3. Or sorry, 8. I don't know, I changed that to a 3. I was probably remembering the last problem. Oops, okay, no mistakes in math, just little accidents to learn from. It's okay. All right, so we get that. We can plug that into a calculator. Now there's a negative here. Does that mean something bad or anything? No, it's perfectly fine. We should think about what this negative is saying. What it's really saying is just that we're to the left of the data point. So the negative z-score just means that the data point is to the left of the mean, but you might still say it's 1.125 standard deviations away. So for example, you would still think of it as equally far from 63 as, let's see, as 69. Sorry, not 63, 60 is the mean. Oops. So you would think of 59 as being equally as far from 60. Sorry, 51 as equally as far from 60 as 69 is, because you would still get the same number, same z-score for 69, except it would be positive. But the point is, the distance is the same. It's just that one of them is to the left and one is to the right. Okay, and I guess I'll do 70 since I said I would, but I already did a third example. Okay, so the z-score for 70, just one more, would be this. Okay, and that's it. So now, what do we use these scores for? What's so nice about them? Well, they let us compare data by removing context. So z-scores let us compare results from different data sets. So here's an example of how this will work. So for example, if one person in one class, I guess I'll call him John. So John gets I don't know, an 83 on an exam. And in that class, the mean was 76. So most people got around a 76 with a standard deviation of 4. So meanwhile, Ali gets an 88. So seemingly already Ali did like way better than John. Good job. But depends on the class. It depends on the average of that class and the standard deviation of that class. So in his class, the mean was 80 and the standard deviation was 5. So you can say in one context that Ali did better than John, but let's think about things in relative terms. So who did better relative to their own class? And the way we can figure this out is we just need their 2 z-scores. Okay, so let's do that. So John's z-score would be what? Well, John got an 83, so that is his data point, 83. And what I'm asking is, how much better did he do than his classmates? So I have to look at 83 minus 76 to see how far above the average he was. But then I'm going to divide that by the standard deviation to see how much better his position was relative to how spread out the data is. Okay, so that z-score it's going to turn out to be, so it's a 7 over 4, 1.75. So that means that John was 1.75 standard deviations above the mean. So pretty good. Not super high above the mean, but pretty good. And Ali got an 88. And in that class, the average was 80, but the spread was a little bit higher. It was 5. So you do this calculation, and you end up with 1.6, slightly less. So this is how many standard deviations above the mean Ali was. So relatively speaking, John did better. But this is still a very simple way of thinking about things. So don't put too much into it. But it is one nice thing to do. So for example, why don't you want to put too much into this? So for example, if I think about like soccer, so I like soccer, right? If I played against a bunch of 5-year-olds, I could probably score 100 goals. And then Messi scores like, I don't know, 50 goals a season or so. So I'm not better than Messi just because I scored more goals than him. And the average number of goals and the standard deviation might be lower. So my Z-score might be super high up, but that still doesn't mean anything in that situation. So you got to be careful. You can't just use this as the ultimate way to decide who's better in different things. Okay. All right, so let's do another calculation example though. So which GPA is better? So other schools do have other ways of calculating GPA. So there's this one, a 2.85, where the mean is 3.0 and the standard deviation is 0.7, or this other weird, I've never heard of a school like this, but a 77 is their GPA if 80 is the mean GPA and the standard deviation is 10. So which GPA is better? So schools do have to think about this, like when they're accepting students. It's very important to think in terms of relative terms, how strong a GPA is. Okay, so we'll just calculate the two Z-scores. So for 2.85, they should both be negative, right? Because they're both to the left of their corresponding means. 77, 80, 2.85, and 3. So if I do this, divide that by 0.7, bust out a calculator so you don't have to do annoying, whoops, should be a 0.21. Okay, and then for the other one, 77, do 77 minus 80, divide that by 10. Negative 3/10 is negative 0.3. So now if you're not so comfortable with negative numbers, you might get a little bit confused right here. Which one of these is better? Which one of them is worse? Well, this one is actually more to the left because it's a bigger negative number. So how do I actually answer the question? So which GPA is better? The first GPA is better. So it's slightly higher, relatively speaking, because it's less negative than the other one. Negative 0.3 is further to the left. Okay, let's see. Okay, that's a GPA example. We'll do one more example. Sorry, I'm Missing some notes. Very strange. Okay. Let's just do this example. So baseball example, the Dodgers just won today, so I guess this is relevant to this lecture. Angels versus Rockies. So here's some data that sports people look at. So I don't know which season, in some season, long ago, the following happened. The Angels, they scored 773 runs, but the mean of their league, so apparently this is true in baseball, I don't know anything about baseball, but there's two different leagues. The mean in this league was 677.4 with a standard deviation of 51.7. And the Rockies are apparently in a different league. So they scored 755, so they scored less. But let's see how they did relative to their own league. So their mean was 640 of that league with a standard deviation of 55.9. So who was better in their own league? We can think about in terms of z-scores. So for the Angels, the z-score is going to be 773 minus 677.4. Divide that by the standard deviation. Doing it a little quicker now that we're used to it. And you get 1.85 if you use a calculator. Meanwhile, the Rockies, their z-score was 755 minus 640 over 55.9. So although they scored less relative to their own league, they actually scored more. So that's another example for how z-scores work. So they didn't actually score more, but they scored more relative to their league. Okay. And that lets us still compare, even though they're not in the same league. We can think of the Rockies as actually scoring more than the Angels because they were in a league that on average scored less, but they were further away from that average than the Angels were from their average. Okay, so I thought this lecture kept going, but my notes have run out. So I guess I'm gonna cut it here. Let me just see what we're gonna do next time. So next we'll look at measures of position some more. So there might be a part 2 video coming up that rely on the median instead of the mean. If it's not here, if it's not another video being assigned tonight, then I'm a liar and we're going to do it later. My notes are lying to me. Okay, but see you in the next video.